I'm happy to present you Simone Brivio, who is AJS for Polytechnico di Milano, and is here to present Autoencoders from reduced order modeling to operator learning. Simone, the floor is yours.
Thank you for the kind introduction, the invitation. I'm really happy to present this. That's an outlook on Autoencoders from a really small niche of reduced order modeling, and then we proceed towards what's more modern in operator learning. Okay, but before starting, a short bio. Okay, so I graduated from Politecnico di Milano following the mathematical engineering course, and then I pushed my PhD at the Department of Mathematics at Politecnico di Milano, and I had the opportunity to visit the research lab, CAM lab, led by Professor Siddhartha Mishra. And then I recently defended my PhD thesis under the supervision of Professor Andrea Manzoni and Professor Luca Formaggia. And now I am I'm holding an incarico di ricerca position at DMAT at Politecnico. Okay, so that's it. My scientific interest lie at the intersection between scientific computing, numerical analysis, and deep learning. In particular, I'm interested in scientific machine learning, deep learning, and broadly speaking, in mathematics for AI to understand, to design deep learning models for scientific computing and computational sciences. So that's it about me. I'm really eager to speak about the research, and that's what's important here. Before delving into the main topic of the research, I would like to lay some background and the motivation that underlies the research. And the background lies on parameterized PDEs. That are a special kind of PDEs that depend on a set of physical and geometrical parameters. And in principle, we would like to compute the solution of this type of PDEs there in the configuration of the physical and geometrical parameters. And of course, this is extremely expensive when considering, for instance, cycle-element methods such as finite element method or spectral element method, because we have to query this high-fidelity solver a lot of times. And that's an excessive computational burden. But these type of problems arise in many applications involving, for instance, optimal control, uncertainty identification, sensitivity analysis, and whatever. So we have to come up with a strategy. And the strategy is to consider surrogate modeling techniques. Essentially, we would like to approximate the parameter map, the parameter to solution map, with a surrogate model that is fast, efficient, and accurate. So the pipeline for data-driven surrogate modeling is the following. We would like to generate a set of snapshots of the solution for bearing the configuration of the parameter and also variable. So we collect this snapshot in a snapshot matrix, and then we design the surrogate. How we design the surrogate from starting from some prior knowledge or some expert opinion or any other technique that you would like to pursue, and then si è bloccato. Sorry. Okay. So sorry for the interruption. So we train the surrogate model with the collected labeled samples, and then we are ready to deploy the model in some application. So in sensitivity analysis, optimal control application, and whatever you have in mind. Today we will focus on a specific part of this pipeline, that is the design of the surrogate. And in particular, we consider a specific subclass of this kind of surrogate modeling techniques that are reduced order models. Reduced order models can be described in terms of a certain specific pipeline. The first element of this pipeline is manifold learning. So we would like to represent the variability of the physical system using dimensionality reduction techniques to get a suitable representation using a few intrinsic coordinates. Okay, and then leveraging this kind of express representation, we would like to devise a latent state approximation. So we would like to devise an algorithm that approximates the latent space. We should do so by means of physics-based methods. So we essentially substitute the latent representation inside the physical equations and then project and solve, or we can interpolate using standard methods or neural network techniques or Gaussian process regression, or any other technique that you would like to consider. The point is that we want an approximation of the latent space, because in the end, we would like to connect the latent space approximation with the decoding to get an inference model. And thanks to this inference model, we are now ready to assemble the model proxy for the surrogate model. So this is the surrogate model pipeline. And in this talk, I will focus on a specific part of this pipeline, that is manifold learning. And in particular, I will focus on classical techniques such as proper orthogonal decomposition, and then move on towards autoencoders. Okay, so proper orthogonal decomposition. I believe that you all know what the proper orthogonal decomposition is, but let's just be precise and introduce the nomenclature that's needed to properly describe what we are doing. So the first thing that we need to introduce is the solution manifold. The solution manifold essentially is a collection of all the possible configuration that the solution can take depending on the value of the physical and geometrical parameters and also the time variable. Okay, and then with this in mind, we set up our dimensionality reduction framework considering a space discrete framework. So we assume that we are in a finite dimensional framework. Okay, so this is, of course, a limitation from a mathematical point of view, but also it's consistent to what we are used to, because essentially we compute a discretization of the solution of the high fidelity equation to get essentially some finite dimensional representation using the algebraic formulation. So this is, of course, a trivial way to proceed. The point is, with this kind of formulation, we can set up the minimization problem for the proper orthogonal decomposition. Essentially, we would like to compute the best rank n orthogonal projector using a metric that is essentially the mean squared error. Okay, so this is very basic. How can we compute the PDE metrics to encode and decode? We use the Cartier-Schmidt theorem. Okay, the Cartier-Schmidt theorem essentially allows us to compute the PDE metrics by means of a closed form solution. And in particular, we proceed as follows. So we collect all the possible configuration of the high fidelity solution inside a very big matrix, that is the snapshot matrix. And then we perform singular value decomposition to decompose the matrix, highlighting essentially the left singular vectors. And we select the first n singular vectors to get the PDE matrix. Essentially, this matrix solves the PDE minimization problem. So this is, outstanding in my opinion, because we can get a closed form solution that's, the best possible solution, the best possible representation using a very simple algorithm that is available in most modern libraries, especially data science libraries and referring Python libraries or whatever you have in mind to use. The point is, this is efficient most of the time because we can set up a pipeline that is based on efficient algorithm, but also consider, for instance, randomized version of singular byte decomposition to speed up everything. But that's not all, only nice from a computational viewpoint. It's also nice from a mathematical viewpoint because we have many pros. For instance, we have a stable decoding. Essentially, this kind of decoding entails an isometry, and that's essentially the same as having a Lipschitz constant equal to 1. That's incredibly useful in numerical analysis application. And also we have some representation consistency. An element of the solution manifold and its projection entail the same latent vector. And that's, useful and is consistent with the fact that we are dealing with a projection mechanism. And then the most important thing is the fact that, of course, we can describe the error in terms of the singular value decomposition, in particular, in terms of the singular values. And this is important because we can reverse engineer this formula to select the appropriate value for n. Okay, so we select the correct value of n depending on some tolerance that we set up before. And this is incredibly useful because we know a priori how much variance we retain, at least on the training samples. Of course, this is very different when considering test or validation samples. However, okay, there are many pros, but proper orthogonal decomposition come with some cons. The main con is the fact that sometimes the projection error and also the Kolmogorov bandwidth decay slowly. And the point is the fact that this type of phenomena for which the Kolmogorov bandwidth decays slowly are very common. And in particular, we can set up very simple problems. This is a propagation of a step signal, and this is a simple wave equation that entails a Kolmogorov bandwidth that decays very slowly. In particular, the Kolmogorov bandwidth decays algebraically with an exponent of 1/2 for this problem, and this is very deadly. What can we do within this context? We need to come up with a strategy to overcome the limitation of the Kolmogorov bandwidth. In the literature, this is often referred to overcome the Kolmogorov barrier. And essentially, the solution is to seek an encoder-decoder strategy in a larger model space. Essentially, instead of minimizing inside the subset of all possible linear strategies, essentially we take the infimum with respect to all possible, in this case, continuous maps that map from the physical space onto the latent dimension in the case of the encoder, and then vice versa for the decoder. Okay, and basically this is very simple. We can set up the nonlinear Kolmogorov bandwidth using this kind of definition over a larger class of model, and simply have that the nonlinear Kolmogorov bandwidth is less or equal than the linear Kolmogorov bandwidth. And okay, this is very basic. We simply take the infimum in a larger class of model. Okay. The point is, how can we parameterize the encoder and the decoder? We use autoencoders. Essentially, we use neural network architecture to parameterize the encoder and the decoder. And we are no more bound by linearity because we introduced nonlinearity thanks to the nonlinear activation. Okay, so this can be ReLU, NH, BQ-ReLU, whatever nonlinearity you have in mind. Okay, so in principle, we are now able to overcome the Kolmogorov-Henry barrier. The point is that we don't know if we overcome the Kolmogorov barrier because we can have some training error, we can have some structural limitation of the model that we are considering, because we can implement autoencoders, as you may know, with dense architecture, convolution architectures, graph architectures, or whatever. The point is that we don't know a priori if we are able to overcome the Kolmogorov barrier. However, we can possibly do it. And the main con is the fact that we lose the mathematical theory that supports essentially proper orthogonal decomposition. That's a strong mathematical theory. So what can we do? We can bridge proper orthogonal decomposition and classical autoencoders by considering a class of autoencoders that are called deep symmetric autoencoders. Okay, so what are deep symmetric autoencoders? Deep symmetric autoencoders essentially try to mimic proper orthogonal decomposition with an autoencoder architecture. So the first thing that we need to do is to recover symmetry. So we devised a decoder architecture that is specular to the encoder architecture. Specularity or symmetry in terms of layer dimension. So essentially, if we map from F4 to F2, then in the decoding phase, we map from F2 to F4. Okay, this is a very basic example of symmetry. So structural symmetry, and also symmetry in terms of Lipschitz activations. Indeed, we use an activation for the decoder that is the inverse of the activation of the encoder. Okay, and this is, that can be a bit of a constraint because, I don't know if you come up, if you can come up with a lot of activation that satisfy this invertibility, but there are many activation actually. For instance, ReLU is a Lipschitz activation that is invertible, but also we can consider specifically uncrafted nonlinear activation, like this is an hyperbolic activation that was proposed in the literature by Samuel Otto and co-workers. But you can devise any kind of invertible activations. The main requirement is the fact that you need to come up with a nonlinearity. Of course, if you use an activation that is linear, then you're ready to go, but you don't have introduced a nonlinearity. Okay, so this is the main point about nonlinearities. So what do we gain? So what's the point of considering deep symmetric autoencoders instead of autoencoders? The point is the fact that if we add constraint, then we recover some nice mathematical properties and also some nice structure. Okay, so starting from the base architecture that is symmetric autoencoders, so SAE, we can add, for instance, orthogonality constraints. For instance, we can add some orthogonality between the weight matrices of the encoder and the decoder, and also adjust the biases consistently to get symmetric bi-orthogonal autoencoders. And we can enforce Forte symmetry in order to get closer to proper orthogonal decomposition, essentially by enforcing the fact that the weight matrix of the encoder and the decoder are parameterized by the same metric, essentially. In this way, we can get something that is incredibly closer to a proper orthogonal decomposition that we call symmetric orthogonal autoencoder. Okay, so again, nice structure, nice mental trick that you did, but what's the point? The point is the fact that we recover properties. Indeed, we can recover some representation consistency that is very similar to proper orthogonal decomposition. And again, we can get essentially Lipschitz control that is independent of the weight matrices, because essentially we are using isometries in the case of symmetrically orthogonal autoencoders. And that's very nice because we can select a priori the activation functions such that we are sure that the Lipschitz constant is less than a prescribed value. And that's very nice in my opinion. And the second thing that's very nice is the fact that we can come up with error estimates. And those error estimates are very intuitive and very explainable. Indeed, if we consider the mean squared error, we can essentially bound this quantity by some sum over the number of layers that depend only on two very basic and very easy to explain quantities. The first is the Lipschitz constant of the decoder activation that's readily available. I mean, we don't have to compute anything. And then we have the projection error at each layer. And that's another thing that we can compute essentially at each layer. Essentially, we take the Fourier paths of the first layer, compute the projection error, take the Fourier paths of the second layer, and again and again. Okay. This is very nice because this is very similar to what happens in the case of proper orthogonal decomposition using the Cartan-Schmidt theorem to get some control over the error using singular value decomposition and the value of the singular values. Actually, we can devise some closed form solution based on this upper bound that closely resembles essentially proper orthogonal decomposition. The point is that this kind of closed form solution is far from being optimal because it is based on an upper bound. In the case of proper orthogonal decomposition, here we would have an equal sign. Okay, this is only an upper bound. So the question is, can we discard this beautiful mathematics? Of course not, because we can set up an initialization strategy based on this closed form solution that essentially is based on an iterated application of proper orthogonal decomposition at each layer to compute essentially an initialization for the weight matrices and also the bias vector that essentially is data driven. That, of course, can be better than essentially initializing the architecture with a random initialization in terms of loss before training, in terms of training dynamics and whatever. The point is the fact that using this kind of initialization strategy, we have essentially a symmetric orthogonal autoencoder because we have come up with a strategy that is based on the fact that we are working with symmetric orthogonal autoencoder. However, this is not a limitation because this is only initialization, and essentially from this submanifold, we can proceed during training depending on the constraint that we have in the architecture. Instead of working with symmetric orthogonal autoencoders, we can come up with a strategy that essentially constrain the autoencoder instead to be in the submanifold of symmetric orthogonal autoencoders, so moving in this submanifold, or without constraints in the bigger manifold of symmetric autoencoders. So this is very nice, very easy to implement, and very explainable, but is it useful? So what can we get from it in practice? In practice, we can get two things. The first thing is the fact that, as you see on the left-hand side, we can get before training, so at initialization, some kind of decay of the validation loss that is very similar to what happens in low rank approximation. Essentially, we can leverage this kind of computation to reverse engineer everything and then set up the bottleneck dimension as function of this initialization. And that's, I mean, that's not a closed form solution, but that's something that can guide us to select the latent dimension. And once we select that bottleneck dimension, we can set up the training. And here we selected n equal 3, and then we trained. And the starting loss is, of course, lower than the standard coming initialization. And this reflects sometimes, not every time, because this is not a guarantee, sometimes reflects also in the training convergence. So it speeds up the convergence. And this is, in my opinion, really interesting, because if we enforce some structure, we can gain some properties, and also we can gain some kind of strategies also to design them. And this is, in my opinion, very important. Indeed, we have structure, we can get properties, we can get some nice things, but also keep in mind that we can lose expressivity, because of course that's not free lunch theorem. If we get a larger class of models, we may have an higher accuracy, or I don't know, a richer architecture, or an easier implementation, or whatever. But if we add constraints, what can we get? We get mathematical properties, some type of guarantees, and some insight on the design of the autoencoder. Okay, so that's it for the first part of deep symmetric autoencoder. In the following, I will challenge another problem. And that's the first hypothesis that we have considered today. And the first hypothesis essentially said that we have considered only reduced order modeling strategies in a discrete framework. Essentially, we have a space discrete formulation of proper orthogonal decomposition, autoencoder architecture, and whatever. The point is the fact that these kind of strategies can be relatively easy to implement in the sense that we can use convolutional autoencoders that are well tested on structured domains and structured meshes, or graph architecture to consider a structured meshes, or whatever you want to consider. The point is the fact that we can lose some versatility. And in the following, I will detail why we need more versatility, in which scenarios we need more versatility. And in particular, we consider autoencoders within the context of operator learning. Okay, so the first scenario would be, okay, I would like to seek resolution invariance. Basically, I may have samples with some kind of resolution, so NH equal 10, and then I have another frame sample with NH equal 20, and whatever. So I want some architecture that without any kind of pre-processing, without any kind of pre-computation, can deal with different resolutions. And also, it may happen that we want to train with a resolution that's, that can be a low resolution, and then test with an higher resolution. So we want to perform, for instance, super resolution. Or we can, we would like to consider a combination of the former. Okay, so this is the first motivation that enable us to consider essentially architecture that are more flexible with respect to the input and output resolution. The second problem is the fact that it may happen that we have point cloud data or sensor data, and the sensor vary in position, or the number of samples vary, or both of them. And this is a huge problem for classical autoencoders, because no discrete formulation can deal with this kind of this kind of problem. Okay, so these are very simple cases. But what I found most interesting in my research is the application of this kind of framework within the context of problems that are geometrically parameterized. Because if the problems are geometrically parameterized, essentially the domain shape depends on a geometrical parameter. And if the domain shape depends on a geometrical parameter, the domain shape changes within samples. And the problem is the fact that we may need a resolution to solve for one sample with some domain, another resolution for the second sample, the second domain, and the third resolution for the third sample, the third domain. So we cannot use standard neural network. We have to implement everything using an integral formulation, something that is based on function spaces. And that's where we need operator learning. Essentially, we formulate everything in terms of function spaces instead of Euclidean spaces. Essentially, a minimal requirement many times is to consider, for instance, Banach spaces, but to be more consistent with the formulation of PDEs, many times to consider Sobolev Hilbert spaces, to be more consistent with the underlying equation. Anyway, we would like to set up the learning problem in terms of learning a function from a function. So function to function learning, instead from vector to vector learning. Okay, so thanks to this, we can set up the autoencoder architecture essentially in terms of infinite dimensional spaces, possibly infinite dimensional spaces, within the context of function-to-function learning. So we have to essentially approximate the identity map in terms of this functional objective. Okay, and that's really similar to what happens in classical autoencoder. The only main thing is the fact that we need to compute on the right norm. So the norm for essentially the space that we are considering as input and output of the autoencoder. Okay, so this is the formulation. I mean, that's really close to standard operator learning, even though this is an unsupervised task. And there are a little bit of technicalities that I don't want to bore you with, of course. But the main message that I would like to communicate today is the fact that we have to come up with intelligent strategies to design these autoencoders. Because, of course, we cannot use standard architecture, as I said before. So what can we use? Okay, the first thing that comes to mind is, okay, we start from the classical autoencoder. So encoder-decoder. This is NH, the number of degrees of freedom. So we are in a finite dimensional space. Everything works out. Okay, so what do we need to consider to move these to function spaces? We have to focus essentially on the outermost part of the architecture, that is the one that communicates essentially with the degrees of freedom. Okay. In the case of the standard discrete frameworks, essentially this is a simple neural network where we have here a nonlinearity. In the output, we don't have a nonlinearity, but I mean, that's the same thing. Okay, so how can we transfer this notion in a continuous space, in a space continuous context? We can simply rewrite the scalar product in a function space. Okay, instead of considering a matrix collecting all the possible modal basis function, we use a set of basis function in an Hilbert space. Okay, and that's the same in the case of the lifting. Okay, so we have projection and lifting. Okay, and this is, enough. Okay, this is sufficient to consider problems with different number of degrees of freedom, or problems with different resolution, whatever. Now, the main problem is the fact that we may need something more to work with problems that are geometrically parameterized, because geometrically parameterized problems are very difficult to compress and are very difficult to approximate also. So we need an inductive bias in the architecture. And what's the inductive bias that we can introduce here? We can introduce an inductive bias, essentially making the basis functions adaptive with respect to the geometrical parameters. In this way, we have a formulation that is continuous, so space continuous, but also geometry aware. The space continuity grants us essentially the versatility to tackle problems that are non-trivial, but the geometry aware part of the architecture enable us essentially to consider problems that are difficult to approximate. And this is the main feature of the architecture. Okay, and then thanks to this architecture, we can set up essentially a surrogate modeling pipeline using manifold learning, thanks to this space continuous geometry aware autoencoder, and then thanks to these coordinates, we can approximate using a neural network starting from the physical, the geometrical, and the time variable onto the latent space, and then set up the inference model in problems that are very difficult to tackle in terms of versatility, in terms of non-triviality of the physics. I mean, here I have essentially a classical benchmark, that is the Navier-Stokes equation with a flow over a cylinder. But the main difficulty that I introduce here is the fact that the cylinder changes position and dimension within samples. And this introduces a large variability of the solution field. So the solution manifold is extremely variable in this case. Nonetheless, I am able actually to compute a very faithful approximation thanks to the surrogate model. In the case of, when considering the whole field case, so in all the channel, but also in a very precise area of the domain, especially in the wake of the domain, that is one of the most difficult region of the domain to approximate. And this is, in my opinion, remarkable in terms of easiness of implementation, because we straightforwardly generalize the architecture from a discrete non-geometry aware architecture towards a continuous geometry aware one, but also in terms of the accuracy. Okay, this is not the most accurate model out there, of course, but it's a model that's guided from the mathematical background that underlies the physical equation, but also it's something that we actually know how to design, know how to set up, that are closer, that is closer to reduced order modeling and the techniques that we are used to. Okay, and that's the same when considering 3D problems. For instance, here we got the distribution of the temperature in a heat exchanger geometry with 14 geometrical parameters, where I parameterize the position and the dimension of the heaters, and also the inlet and the outlet. And also we have 6 physical parameters to make everything more complex that govern the temperature on the heaters, the viscosity, the diffusion coefficient, and whatever. And we can see that for 2 different configurations, here I get an approximation that is actually very close to the ground truth, both in a more diffusive and a more advective case. Okay, so that's the end, more or less, of the autoencoders in function spaces for geometrically aware, for geometrically parameterized problems. So, what have you done today? Today, essentially, we have provided an introduction, a very classical introduction to use of the modeling, considering the relevant aspects of manifold learning, for instance, proper orthogonal decomposition and autoencoders described from a very classical setting. And this duality between POD and autoencoders enable us to develop an architecture that is essentially a bridge between the mathematical structure of proper orthogonal decomposition and the expressive power of a neural network architecture that parameterizes autoencoders. And this led us to the development of deep symmetric autoencoders. Deep symmetric autoencoders are extremely effective into maintaining some mathematical structure and also to guide us into the design of more, let's say, carefully designed architectures in terms of some kind of criterion based on error estimate and whatever. The point is the fact that we have highlighted the fact that if we introduce some structure, we may face something when considering like expressiveness, approximation accuracy, or whatever. Anyway, structure sometimes is good, especially when needed in the case of dynamical systems or whatever is your application. The other problem in the case of autoencoders that we needed to tackle is a versatility problem. So we needed some versatility to consider problems that are geometrically parameterized, but also when we would like to consider a distribution invariant architecture or architecture that can take different point clouds with different cardinalities and whatever. The main point is the fact that autoencoders can be readily merged with operator learning techniques to devise architecture that are more flexible. Okay, and this has enabled us to consider and tackle effectively problems that are non-trivial, like Navier-Stokes channel problem, also the heat exchanger in a complex, let's say, relatively complex 3D geometry. Okay, so that's it. These are the main references. Again, it has been a great honor to present today, and thank you again.
Are there any questions?
Thanks for the talk. I have a question about continuous autoencoders. So essentially, understood correctly, the way you extend autoencoders to the functional settings by fixing a basis, choosing a basis which is continuous. My question is, if you forget about geometrical parameterization and just assume, for instance, that you have a fixed grid, so in a setting in which you use PD or classical autoencoders, have you tested, like, have you an idea of the computational cost of using continuous architectures compared to discrete models?
Okay, thank you for the question. Actually, it's a very interesting question, in my opinion, because you have raised a problem, of course, because, okay, what are these? These can be neural networks. We can parameterize them using neural networks. And the main problem is the fact that when compared to the discrete counterpart, here we got a single matrix. And again, a single matrix. Of course, these can scale up badly in terms of the number of degrees of freedom, but I mean, that's the only point. The point here is the fact that these can be as bad as you want. I mean, they can take and merge information from spatial coordinates, and that's even worse in the case of geometrical parameterization, because we need to devise an embedding for the geometrical parameter to be injected into the input of the modal basis function. Alternatively, another possibility that I've not investigated actually is to use, for instance, spectral basis function. Why not? In this case, a very simple case without geometrical parameterization. So we can, I don't know, Fourier. Why not? Or we can compute the mean, the variance. The point is you can set up an algorithm that is actually based in function spaces instead of simply doing a matrix vector further. So in terms of number, because you are interested in numbers, I suppose, I think that from 1/3 to 1/2 of the parameters of the architecture were devoted into the approximation of the modal basis function. The point is you can add actually the number of parameters by considering the same basis function in input and output. That's not a problem, and that's actually my implementation. So I use an implementation that reports the same basis function as input as output. I had not seen in my implementation, of course, some advantages in considering different basis functions, but I assume that's because I considered this test case is so maybe problem dependent. Or another thing that comes to mind is the fact that the point is the fact that the number of data were like in the order of 100, 150 different configurations. Maybe if we need, if we provide more data, then we may need different basis functions because I don't know, more data we can scale up with expressivity. So never scaling those can maybe enhance your application, but I don't know. I mean, I work in a data scarce context.
Then I saw Gabriele, maybe.
Yes. I guess my question was very similar to one by Lorenzo. So, if I understand correctly, your basis functions are actually neural networks, neural architectures as well. And so, how do you feed the genetic information to those? Like, how do you condition your basis based on the geometry? Would you want to
Thanks for the question. Okay, the main point that I overlooked here is the fact that I know the geometrical parameterization. Okay, so it is an explicit geometrical parameterization. It's something that I can measure at least, or in the case if I'm the one that generates the data, I can set up some framework with free-form deformation, radial basis function, mesh motion, everything that you can use to parameterize the geometry, so to represent the geometry before. And so in the case of the test case that I showed today, yeah, we got the position and dimension of the obstacle. Okay, that's I mean something that we can set up. And I would like to highlight the fact that in the data generation phase, I don't use mesh motion. I don't use free-form deformation, even though I can. because I don't want to get the. I wanted to show that the method I implemented was something that was very versatile. So I didn't want any kind of structure beforehand that comes from free-form deformation. Instead, I simply generate different meshes without any kind of information, and then I get the position and dimension. And in the case of the text changer, that was the same. Actually, of course, another problem that comes to mind is okay, if we don't know how to parameterize the geometry, or if we are provided at least I don't know, a point cloud, a mesh, and we need to estimate the geometrical code, and that's another point that I'm investigating.
Do you have any comparison with respect to what happens if you mesh, do mesh motion? And
Sorry?
So do you have any comparison in terms of results of what happens if you say use the standard autoencoder or something on different cases with the same mesh topology?
Okay, yeah, I have them actually. I can see if I. Okay. This is no. I even got no. I don't have it. Okay, this is the one. Okay. Essentially, what have I done here? I have measured the mean squared error in the case of PDE projection and continuous, say, non-continuous geometry web basis function using a brute force approach. So essentially, I have generated for the same geometrical parameter a set of physical parameters in a grid-like manner, and then I computed the proper orthogonal decomposition for each instance of the geometrical parameter. And this is the mean squared error with an average with respect also to the geometrical parameters. I don't know if I was clear, but I mean, that's more or less the PDE error, but for continuous geometry awareness. And this is the PDE projection. In the case of the problems that I've been considering. The point is the fact that this is a brute force approach, essentially generated with respect to a criterion that is the worst case scenario. In practice, we train them with mean squared error, also with respect to geometrical parameters, and we get a trend that is more or less what it is. The main point of this trend is the fact that we get to saturation actually before when considering a continuous geometry aware approach, then when considering a POD aware approach. And in my opinion, that's the whole point of architecture, because we need less basis function to get the most information. Okay, and also be aware that we get an accuracy that is lower in the case, sorry, a relative error that is higher, so it is lower, so the accuracy is higher. Okay, so this is more or less, I don't know if I've answered to your question, but of course, yeah, you can set up the whole pipeline in the discrete simply by, deleting the space continuous framework and essentially parameterizing the weight matrix by means of the geometrical parameters. And that's very, I mean, that's quite close to what Nicola Franco does in the case of deep orthogonal decomposition.
I have just a quick question, very basic, I think, about the comparison between discrete and continuous. Like if you assume there is no geometrical dependence, so you have only the two models, like they are quite equivalent, right? Because in the first one, you give the network some snapshots of the solution. In the second one, you give the projection on the basis function, but they are like in terms of number of layers and also number of initial points you give to the network, they're quite the same. Or am I wrong? Just
Okay, thank you for the question. Actually, yeah, they can be equivalent if you, of course, set up some hypotheses. Like to get equivalence, we need the same number of degrees of freedom, the same position, the geometry that does not vary. So in that case, potentially, we could have the same. Of course, this is only potentially because in the training process, everything smooths out. I mean, if we get very an high variability for W1 and WL in the discrete case, that's probably a reason. I'm not an expert of optimization, but that's probably a reason that everything smooths out in the previous process. So we get model representation that are, I mean, quite smooth. I have an example. These are basis function. Okay, the second, third, and fourth column basis function, and everything is very smooth. I haven't tried it for this test case, but I assume that if I visualize the basis function for this test case, I mean, it may be something different from this.
For the very interesting topic. I have a couple of questions regarding the deep symmetric autoencoding, particularly constraint. So you said that you can actually obtain some nice properties such as symmetry or flip chip property by just making wise choices regarding the architecture. And correct me if I'm wrong, I believe that these conditions are actually enforced, like the architecture is built in such a way you obtain these things. I was wondering whether it could be also at least a nice attempt to try to retrieve the same condition, the same properties by softly enforcing this condition, meaning adding some loss regularizer terms that can actually lead to similar properties. Maybe symmetry is mostly achieved, not 100%, but in a soft way, so that the model is more flexible and tries to recover the same.
Very interesting question. That was the start of our investigation. Oh, okay. Okay. We have had very simple models at the beginning, and we have tried to train them with this criterion, also enforcing both the soft and the hard constraint. Only the soft. The point was that we saw almost instantly that the fact that we, in the case when we enforce the constraint as a hard constraint, it was incredibly smoother in terms of training convergence. And of course, the second point is the fact that, hard constraints comes with a cost, of course, because you have a parameterization. Essentially, you are performing gradient descent on a submanifold of the big manifold of autoencoders, and the parameterization is quite involved. And indeed, this is the training cost when considering. Let's take the first test case. This is the standard autoencoder. This is the symmetric autoencoder. Essentially, we use a little bit less time because actually the activation cancels out in the middle, but I mean, more or less they're the same. Okay, symmetric orthogonal autoencoder, we parameterize for each layer 3 orthogonal matrix that depend on essentially the number of degrees of freedom. Okay, I mean, that's quite intensive in terms of training cost. Of course, you can get less good result in terms of accuracy, because here we get very low accuracy when compared to all the other alternative if you enforce the not by design but as a sub constraint. And the second point that we decided to use a constraint because we wanted at least once something that worked by design. I mean, we are sure that the properties are set from the start to the end of the. Of course, again, scaling is a matter of compromising, in my opinion. So you can use them.
Oh, sure. Can I proceed with other questions? No, thank you for the explanation, and that actually I think leads to the also a nice bound on the error that you get. If that is architecturally enforced, you can get to that result. And about that constraint, bound, sorry, in a way that depends on the Lipschitz constant, which again depends on the activation function. And you said that there is a vast class of activation function which can satisfy the bilateral Lipschitz property. But I was wondering if in practice there is actually a subclass of this function which is satisfying the property and still leading to, in general, or depending on the problem, to better results. So if there is actually a go-to choice for the Lipschitz function.
Thank you for the question. Actually, the choice of activation function is fundamental. Okay, minimal requirements, invertibility, whatever. Okay, the main problem is the fact that these are all minimal requirements. Of course, these error bounds suggest us to take an activation function whose inverse as a Lipschitz constant that is less or equal than 1, because the problem in this case with the fact that if we use L layers in the encoder and the decoder, we end up with a bound that depends on 2 times L power of the Lipschitz constant of the decoder, and that's really bad. I mean, take L equal to 3, that's quite low, and then we use the decay activation with the classical alpha equal to 0.1. We elevate by 2, and 2 again, because L equals 3, so again, more or less. So 0.1 to the power 4, sorry, I'm wrong. Of course, not 0.1, because the inverse, of course, 10 to the power 4, and 10 to the power 4, everything goes up, of course. So the point is to select an activation function whose inverse, okay, so in the case of Licchiarello, I need to select essentially Licchiarello with alpha equal 10, for instance. In this case, if I invert it, then I get a Lipschitz constant of 1. Okay, and then 1 doesn't propagate numerically.
Would you replace like Lipschitz functions with locally Lipschitz function that if in a way you can control the range of the output of a layer? For instance, you just put some positivity preserving architecture. You can just work in a neighborhood on a right neighborhood of 0, and hopefully it doesn't explode too much. And thus the bound of the Lipschitz constant is a bit loose. So I mean, you have the correct bound, of course, but in practice, the bound you observe is way lower. would that be a attempt?
Okay. Thanks again for the question. Of course, that's no guarantee a priori on the tightness. Okay, I can give you a partial answer that stems from theory and is not a proper answer to what you have described, but it's another interpretation of what I wrote here today. Okay, I got both an upper bound and a lower bound. The upper bound depends on the activation of the decoder, and the lower bound depends on the activation of the encoder. Depending on what you need to use this one for, I don't know, you want some guarantees on the lower bound, you can make some choices, or you want some guarantees on the upper bound, you can make other choices. Of course, this reflects us also to the training procedure, of course. In this case, okay, here you got, okay, you see validation MSE and validation loss normalized data. In this case, they are the same because the data are normalized for this specific test case. So we start from like 10 to the power 0, and then we end up with 10 to the power -3. So we get more or less in terms of mean squared error, 3 order of magnitude in practice, and this suggests us what? Suggests us that the boundary was not done in this case, but the choice of activation was good for initialization and also for training. So a matter of, I mean, that's not proper trial and error, but theory guided trial and error, of course.
Thank you very much.
We are far from reaching the same level of rigorousness in the case of POP, of course.
Donald, you have a question?
Yes, I have a couple of questions. Very nice talk, by the way. Thank you. One was on exponent of ellipses, and you already answered. The other one is on second part. Basically, standard discrete autoencoders are when you choose W as directed pulse. If I have to imagine standard autoencoders in your framework, right?
Yeah.
And but with your method, you have to decide a priori which is the finest resolution, and then you put 0 in the output of the first layer when you use coarse resolutions, or you have some strategy.
Okay, so thanks for the question. It's actually interesting. The point is, okay, you meant in the geometry work case, or
No, even without geometry.
even without geometry? Okay, let's
be
not.
different meshes.
Okay, the point is, I can use a criterion based on essentially POD to set up the dimension of the first layer, essentially POD more or less Kolmogorov width. So it is somewhat guided by the POD. So I can use the same number of POD modes to set the number of space continuous modes. Okay, the point is the fact that here I have a certain number of modes, and in the middle I could use essentially whatever I want. I could use I don't know, convolutional architecture in the middle, because convolutional, I don't know, scales better. Or I can I don't know, expand the coefficient, always getting a very compressed representation space. But I may even expand those two. That's no theory on that. The theory I provided was only concerning the outermost layer. Of course, in principle, I mean, it's not the theory, but intuition that may guide us to, I mean, this is 60, this is 40, this is 10, this is 30, this is 40, this is 60, more or less. However, no guarantee in terms of convergence and whatever. Essentially, we decide the number of layers, number of neuron for each layer in terms of the problem that we consider. In practice, as a suggestion from personal experience, the decoder most of the times needs to be, I mean, more expensive in terms of number of parameters than the encoder, simply because it is simple to encode and it is difficult to decode, more or less. Even though we are very used to the fact that in the case of 3D, it's the same, but in the case of nonlinear compression, that's not actually the same. And okay, the reduced network that we use to approximate the latent state, depending on the problem, depending on the complexity of the representation, depending on also on the bottleneck dimension, needs to be complex. Because from, okay, if I have a very smooth latent state, then, okay, I'm free to use a very simple neural network. But if I select a bottleneck dimension that is too low, then I get something in the middle that is can be rough. And then I need to use a very complex neural network to approximate it. But again, this is not some theory guided mechanism. It's trial and error. The whole point is the fact that any type of choice that you make for the encoder and reduced network can be mostly good. The most important part is the fact that we need to parameterize well the modal basis function, because if we don't parameterize well the modal basis function, essentially convergence is never achieved. So the main point is the following. And to conclude, another curiosity that you maybe...
But I mean, you can change also in time. Because you mentioned that you mentioned to apply this.
Possibly, okay, my test case is not, but possibly can change in time. Okay. I think the algorithm worked flawlessly, also in the case of time variation of the mesh. Okay, I mean, during training, that's not a problem because time can be treated as a geometrical parameter, whatever. During testing, the main difference is the fact that you need to have the degrees of freedom of the mesh that you change at each time step. That can be intensive if the number of degrees of freedom is extremely high and you have to collect all this information beforehand. However, depends on the application. If you would like to change mesh, also in the archivality case, it is quite expensive. So the things that you did in the archivality case transfer directly into the approximation case.
Okay, I would close now as we are already 15 minutes late. So let's thank Simone.